So you know the very basics of alignment, checking where in the genome the reads come from. Nowadays, very common format for RNA-seq raw data is the Illumina paired-end data created with directional protocol. That was a lot of words, so let's break it down. Having Illumina paired-end data means that you have two reads coming from the opposing ends of the RNA fragment. This means that you have two fastq files per sample, R1 for the first read and R2 for the second read. The reads are always in same order, so the reads on the first line form a pair, and so do the reads on the second line and third, and so forth. Note that depending on the sequencing device, you might actually have multiple R1 fastq files, and as well multiple R2 fastq files. But worry not, the aligners can handle these. The Illumina reads are always of the same length, so read 1 and read 2 are always, for example, 100 bases long. But the size of the initial RNA fragment, so the insert, may vary, and thus the inner distance between the two reads is often given as a parameter to the aligners. How about directionality or strandedness? The term ambiguous means that the read maps to a location where there's more than one gene. Nowadays, many of the library preparation methods can preserve the information from which strand the read originally came from, which of course helps with these ambiguous situations. These methods are often called directional, stranded, or strand-specific. This information needs to be given to the aligners as a parameter. To be able to select the right parameter for your data, you first need to know which library prep method was used when generating the data. In general, there are three types of library preps. Unstranded, where you don't know from which strand the read is originally from. The second strand, where the first read of the pair, or in case of single-end reads, the only read, is from the transcript strand. And then there's the first strand option, where the first read, or the only read, is from the opposing strand. As you can see, the parameter naming is incoherent and can be very confusing. This is why we have gathered a help page where you can check which parameter works for your data and for your library prep method. So here we have listed different kits and the corresponding parameters. We also have a RSeQC tool in Chipster, which you can check the parameters. This tool can be found in the quality control category, and it will align a small section of reads in your fastq files and determine the directionality of the reads based on that. The report looks something like this. In this case, the data was single-end, and 95% of the data shows evidence that the stranded library prep method was used. In this case, it seems that the read is always on the same strand as the gene, which means that these are the correct parameters in the following tools. It is crucial that you choose the correct parameters. If you use wrong directionality parameter in the read counting step with HTSeq, the reads are considered to be from the wrong strand. This means that in the case where there is no gene on the other strand, you won't get any counts, and if there is a gene in the same location on the other strand, your reads are counted for the wrong gene. Here you can see that we have two files for this one sample, read1 file and read2 file. To find out the strandedness of this data, we select both of the files, and under quality control, we select the RSeQC tool. In the parameters, we need to assign the files correctly. So for read 1, we select R1, and read 2, R2. This data is from human, so we select the correct genome here. You can also give your own genome as an input file here. Now we run the tool. Since this tool is doing a small alignment, it will take some time to complete. As a result, we get a text file and a PDF. In the PDF, you can see an estimation for the inner distance between the reads. In the text file, you get information about the data. This data seems to be unstranded, and these would be the parameters to use in this case.